Okay, so concept chapter 5 due this weekend, mini project 4. Where the focus of mini project 4 is really not just on the kind of niche preserving techniques, but niche preserving techniques in the context of multimodal optimization. So there is, we did talk about diversity in mini project 3, and you can certainly make use of things you've used in previous mini projects for mini project 4, but really the focus for mini project 4, and I'm going to turn on another light here, is an idea of a multimodal optimization problem. So the optimization objective that I used in mini project 1 is an example, especially if you like expand it to go over a larger range. Then you've got a lot of local peaks, and so, a project could be to take a GA, a standard canonical GA without any of these fancy niche preserving, diversity preserving techniques, and run it on that, just like you did in mini project 1, show that it converges roughly to one peak, and then turn on those, and then show that instead of getting a population that is at one peak, kind of, dripping down the sides of that, you get small clusters at the top of all of the peaks. Like that would be, a nice little example. So that's kind of looking for that mini project 4. And then you're forming your partners for your projects. So I think I've had to, due to numerical reasons, there may end up, depending on, we'll see how things shake out. There may be a need to form a 3-person group, but generally it looks like from I think with a number of people left over, that I think we should be okay, that there should be possible for everybody to form pairs. If you're having trouble finding somebody else, again, you can look on Ed Discussion or the discussion boards on Canvas, post on Slack. You can use the people link that's on Canvas, and then that spreadsheet that I posted. Those are all sort of ways to hopefully kind of link together. So any questions about announcements moving forward? Okay, any questions online? Doesn't look like it. All right, so we left off last time talking about introducing bacterial foraging optimization, which actually is an algorithm that my advisor, Kevin Passano, came up with. But I don't know if I ever actually talked to him anything about bacterial foraging optimization when I was in Kevin's lab. BFO. So this is something from Passano. And what we'll see with bacterial foraging optimization is it is inspired by E. coli. So E. coli bacteria. But it also sort of, so it ends up kind of combines the chemical communication, like ACO, with population dynamics, which is kind of like the GA, in an attempt to kind of get a mixture of all of these different features. So I mentioned last time that these little E. coli, if you put them in a petri dish, you notice that they have these these sort of stretches where they'll go straight, and then they'll randomly kind of reorient, and then go straight and then reorient, and so on. And if you were to draw a little E. coli bacteria, it would have all these little flagella coming off of it. And I think in E. coli, these flagella come off all over the body. And there is a little molecular switch inside the E. coli that allows them to turn flagella either counterclockwise or clockwise. And the way they're mechanically structured, when you turn them counterclockwise, you get forward movements. And when you turn them clockwise, you get kind of a random turbulent reorientation. So I'll say like turbulent reorientation. And this forms the basis of the run and tumble. So if you do have sort of like a petri dish or something with food at the center, if you let that food kind of diffuse into the medium, then you end up getting this kind of concentration gradients around it. And if you are a bacterium inside here, if you're to watch that bacterium, it will sort of move in directions. And when it tends to go downhill, it more oftenly reorients and goes in a random direction. And it'll go in that random direction for longer periods of time when it's going uphill. But it will always eventually reorient. So it doesn't go in perfectly straight lines forever. But again, if it was to reorient and go downhill, it would end up reorienting pretty quickly to go uphill again. So you end up getting mostly uphill movement, periodic downhill, and so on, so that it can end up climbing these concentration gradients. So it's sort of a greedy, that term was used earlier, approach to climb concentration gradients. Now there are, yeah.
What would be the heuristic that we use to like basically say, switch directions randomly faster when you're going downhill, but switch directions less often when you're going uphill?
Well, I'll show you the algorithm for the BFO, how it implements it. So I'll get to that in a second here. But this is just sort of the basic idea here. Now, there are some bacteria move around in different sorts of ways. There are other bacteria that have this. So this idea of climbing chemical, we're going to call this chemotaxis. So taxis is kind of like movement. And this is like chemical or toward chemical. So you might hear about phototaxis, that's like movement towards light, scototaxis, movement towards dark, chemotaxis, movement towards chemical. So this is movement towards the chemical. So it's, so we'll call this in the algorithm the chemotactic loop. And so this allows it to kind of climb these gradients. The downside of this is in a simple petri dish like this, where the food's in the center and you get this nice kind of monotonic gradient, then you land where the highest concentration of food is. But if you're in a much bigger space, then there might actually be other patches of food or clusters of food elsewhere that if you focus on this one, you miss out on those other ones that are richer. So this is just a gradient climber. So, as a gradient climber, means that it can be trapped, so subject to local traps. And so in order to get around that, then in BFO, so what these bacteria do is they not only respond to these nutrient gradients, but they actually put chemicals into the medium around them. They put chemical communication. They've actually put signals into the medium for both that repel other bacteria and attract other bacteria. And this leads to bacterial aggregation. So this allows bacteria to sense that although they have found a good food source, there's a bunch of other bacteria elsewhere that apparently are not here, but there's kind of they can sense that they must be somewhere around because they can sense their attractants. And when they get close to those bacteria, then they don't want to cluster on top of the bacteria. So there's a way for them to be kind of from far away attracted to the bacteria, but then locally can kind of stay apart from them. So it's a way to be kind of attracted into regions where there's a lot of nutrients, but then search those regions once they get there so that those bacteria can keep moving around. So we add social communication, kind of similar to ant colony optimization, to help advertise the good things that other individuals have found. So in ant colony optimization, every iteration is kind of a new random draw from this probability distribution. And because the probability distribution's got variance, then some paths tend to go into areas that haven't been gone into before. And if those happen to be very profitable tasks, then they lay more chemical there. And so in the next iteration, that chemical causes more samples to move in that direction. It's a similar sort of idea here. So we're using chemical concentrations to move the population around. Now, what we're also going to add to this is, since we have a population of these things, then we're going to think back to kind of genetic algorithms to a little bit, and we're going to be able to add a selective pressure where we'll have rounds where we periodically kill off bacteria that have not done very well in their lifetime, and then allow bacteria that have done very well to clone themselves. And then we'll also have these dispersal events where we'll just move bacteria from one point to another, as sometimes happens. You get these biophysical relocations of bacteria. You imagine, if you were to blow over some liquid, or if there's some waves or something, you maybe get these things moving around. So it's kind of the idea of having these sort of fine scale mutations and large scale mutations we'll kind of get into here. But this is the inspiration for it. It all kind of comes from this idea that individual bacteria are good gradient climbers, and they can use chemicals to attract each other around so they can share information. So with that in mind, what does basic bacterial foraging optimization look like? And so the basic structure here that is going to depend upon a cost function that is sort of spatially embodied. So we're going to view, basic bacterial foraging optimization structure. We say that each bacterium has a position, and just to be consistent with, I think, Kevin's notation, I'm going to use theta for that position. I'll call it theta I, superscript I. Kevin likes to use superscripts. Where this is just going to be our decision vector. So this will be like theta I1, theta I2, theta I. Oh, right, I'll use D for, so this here is a D-dimensional decision vector. And this here is, we have S bacteria. So I is in 1 to S. So we have S bacteria. And so these positions, we're just moving around positions, and those positions are candidates for the problem we're trying to solve. And so we are focusing on a minimization problem. So, of course, you can turn any max problem into a min problem, just with a negative sign, but this is written in terms of a minimization problem. So each bacteria is going to pay attention to both an optimization objective evaluated at that position in space, as well as these chemical, these cell-to-cell communication between the bacteria. So this is a little bit different than a GA. When a GA, every individual's kind of, their genotype stays with them. But in this case, the bacteria are like individuals climbing around a space. So the bacteria don't, like, the position doesn't live with the bacteria. They move from position to position to position. And each position is kind of favorable or unfavorable in terms of our optimization objective and the cell-to-cell communication. So each bacteria senses, I'll say bacterium I senses at each position this function, which I'm going to be, it'll be J, which will be our optimization objective to minimize. Plus, maybe I'll move this plus over a little bit. I don't know how much space I'll need for this. Plus this long term, which I'm going to call, I'll just notch out a space for it, JCC, which is our cell to cell communication. And so that is going to take this form where it represents all of the attractants and repellents that have been put into the space by the other bacteria. So, so this will be a sum over all of the bacteria. Of an attractant part and a repellent part. And I will do the attractant part first here. So I'm going to do a negative, then a hyperparameter deattract, which is kind of like the amount of chemical put into a medium by a bacteria. And then that is going to be scaled by an exponential, where I'll do minus omega attract. And I'm just going to abbreviate it ATT there, but you could write that out as attract if you'd like. And then this, which is just going to be the sum of squares. So I'm going to write this out as M equals 1 to D of, this will be the position. I'm going to drop the subscript for the current bacteria, or the superscript for the current bacteria. So this is the current bacteria's position at dimension M minus the position of the remote bacteria. So this term here is really nothing more than just theta M minus theta M I transpose, oh, sorry, it's more, the sum is nothing more than theta vector minus theta vector I transpose times theta vector minus theta vector I. So this is just the sum of squares, sum of squared differences. Yeah.
What was the vector theta? Not theta I, but theta. Like
well, so this is for simplicity here, theta is position of current bacteria in this control, I don't know, in this execution step. And yeah.
So in the case for the, when you're doing that, the inner summation, when your I is the same as the current one you're executing, you're gonna get 0, right?
Yeah, you'll get a 0 here. And so this is modeling that the current bacteria is dumping into, because of the exponent, the 0 will turn this thing into a 1. And so the current bacteria will sense its own attractant in this formula here. You could imagine modifying this where you could exclude the current one from the sum. I don't know how much of that would change. I think that's actually was done on purpose so that you have a little bit of inertia where you actually kind of want to stay where you are. But if there's a lot of attractant elsewhere, you'll then be pulled towards them. And I'll say this is just for clarity. All right, and then that sum, and I guess I could put brackets around this. Maybe I'll put a large parentheses here. Maybe I'll put it in a different color just to make it clear. All right, and then the repellent part, which would be same format, but with repellent. So I'll do H rep for repellent times an exponent minus omega repellent times the similar sum. And all the rest of this is the same. And I think all I need is this guy. So if we look at these, so we've got the attractant part here, the repellent part here, and it's kind of no mistake that this is modeling the diffusion of these chemicals away from the bacteria. And this form should look familiar to you because it's borrowed from the Boltzmann distribution. And so we've talked a lot about the Boltzmann. So in a lot of physical processes, when you're talking about if you give things a little bit of energy, how far do they get away from you just with that little bit of energy? And so a little bit of them will get very far away from you, not that much, but most of them stay close to you. Well, and that was modeled by the Boltzmann. And so that's effectively what this is too. And so a lot of times when you see these exponentials show up in physical formulas, it's because the kind of assumption is that we are sitting at some equilibrium where we're sort of asking at the current kind of thermal equilibrium, how far could things have gotten away? And so we can kind of have similar sorts of interpretations where we consider like this thing to sort of be related to kind of height of a pulse, I guess, a chemical pulse. Then this thing here is sort of related to the width or inverse width. Inverse of a chemical pulse. The same way that when we were writing this in simulated annealing, then we would have some measure of energetics. So, you know, in that case would be like, how much energy do you need to get here? Well, if you sort of imagine that it's hard to get very far away from you, then this is kind of a, you know, how much energy do you need? And then you can imagine instead of being multiplied by something, it could be divided by the inverse of this. And so in the Boltzmann, it was divided by KT, and KT kind of represented, you know, if you gave it a lot of temperature, then you could get very far away. And if you gave very little temperature, you couldn't get very far away. And it's the same sort of idea here, but it's just the inverse. And so for simplicity, you made it all multiplication. So if you make this thing equal to 0, then it's not at all sensitive to distance away. If you make it equal to like infinity, it's very sensitive to distance away. And so the kind of smaller this gets, the wider the chemical hump is, the bigger this gets, the narrower the chemical hump is. So this is what the bacterium will be sensitive to, the thing we want to actually optimize, and a communication vector that because they're trying to minimize this whole thing, this will cause them to be attracted to large concentrations of attractant, and it'll cause them to be repulsed from large concentrations of repellent. Yeah.
So when you give the example of how it could be attracted to itself in the first part of the summation, and based on the same thing, could it repel itself? So,
yeah, right. So so if in the kind of the simplest version here, then yeah, there is sort of, if this thing drops to 0 and this thing drops to 0, then there is this kind of bias term, which is the attractant, its own attractant plus its own repellent. Now, if you've tuned these things so the attractant and the repellent are equal, then for the individual bacteria, they fall out because this will be 1, this will be 1, so then it'll just be H rep minus D attract. If those are equal, then for the individual bacteria, it's nothing. Right. But we usually imagine here that we're going to have, you know, a lot of bacteria. So in a natural system, you would have the D here, the D dimension would be very low, would be 3, right? 3-dimensional. But then S in a natural system would be very large. You know, it could be like 1 million bacteria in a small space. But in our optimization, our metaheuristic, then it would be the flip of that, where our S will be relatively small, like 100 bacteria, but our D might be very large, like 1,000 or something like that. So, so it's moving over this larger space. Okay, so this isn't the whole algorithm. This is just the optimization objective that the algorithm will respond to. So every time I move a bacteria around, I evaluate this thing. I evaluate, you know, the objective we care about, and then the communication. And notice that the communication changes based on the relative position of all of the other bacteria. So this creates kind of a cell-to-cell aggregation pressure where they don't want to get too close because of that repellent, but they don't want to be too far away from each other either.
So the whole thing is like the fitness function.
The whole thing is a local, it's a proximate mechanism for bacterial movement that ultimately we hope will lead to higher and higher fitness allocations. That we hope it will cause these bacteria to move to higher fitness. But I don't want to call it a fitness function because this here really is a chemical mechanism just to get these things to move. So it's trying to move uphill here or down, I guess it's a minimize, it's trying to move downhill here, but it's also trying to move relative to these things. But I don't want to give this is really saying is bacteria want to be close to each other, but not too close. But of course, we, as the one who's running this algorithm, we don't care how close our positions are, but we're sort of hoping that by making them attract to each other with a little bit of a boundary, that this will improve their search characteristics so they don't just get stuck in local traps. Okay. So what we're going to do next is we're going to implement the run and tumble based off of this sensed objective. And then we're going to implement those 2 other phases where we kill off some bacteria, cause them to reproduce, and then we spread out some bacteria probabilistically as if a physical process came through and kind of shook up the petri dish. All right, so any questions about this? Pretty clear so far? Just implementing cell-to-cell communication. Okay. So BFO sort of has 3 stages. There's chemotaxis. There's reproduction. And then there's elimination, dispersal. And for all of you typesetting grammar geeks out there, this would be truly a hyphen here. Normally you would think of this as an N dash, but in this case, we actually are saying it's a type of dispersal that we're using to eliminate. It's not an elimination and dispersal. It's a way we're kind of doing elimination with dispersal. So it's a true hyphen there. So the way this works here, and there are some hyperparameters associated with this. And so for chemotaxis, we're going to have like NS up to NS steps in one direction. But then we're also going to have up to I don't think it's up to, it's actually exactly NC rounds of chemotaxis. And then wrapped around all of that, we've got up to, I'll just say NR rounds of reproduction. That then also kick off a new round of chemotaxis every time we do a new one of those. And then elimination dispersal in ED rounds of elimination dispersal. So those are hyperparameters here, which are basically termination conditions. So we can also come up with, so these are simple termination conditions. but you could embellish these. As desired. So we're just going to terminate these things when these counters count down all the way. So the first round, the kind of the most important round, or the kind of focal point of this algorithm, is the chemotaxis round. So in chemotaxis, we say for each bacterium, we're going to do this run and tumble. And so how do we do that? Well, we actually do the tumble first. So the idea here is we're going to choose a random direction, and then we're just going to keep moving in that direction, either until we run out of steps or until the concentration gradient goes up, the cost goes up. And so, because the ideal is to minimize cost. So we either get to our full length, or we get to the first point where the cost goes up and then we stop. So that's what we're implementing here. So how do we do that? We do the tumble first. And to do the tumble, computationally, we're just going to choose a random vector from the unit space from -1 to 1, and then normalize it across all the dimensions. So the way I would write that is I choose a random unit vector which I'll call delta vector divided by norm of delta vector, where delta vector is just drawn from uniformly distributed numbers, a d-dimensional random space here. So we're just saying it's just d variables drawn uniformly from -1 to 1, just the Cartesian product of all of those. That's what we just choose there. So you just draw d random numbers from -1 to 1. You take that vector, you get its length, and then you divide every element by that length, and that gives you a random unit vector. That's how we generate random directions in space. And then from there, now that we have our random direction, then we can run. And so we, again, focusing on just this bacteria, I'm going to move theta I vector to a new position, which will be its previous position plus a step size, which can vary by bacteria. So just to keep it general, I'll say CI, but in practice, just a single step size is fine, and times our unit vector. Where CI is step size. And so that's a hyperparameter. And then from there, I'm just going to reevaluate evaluate this cost function J plus JCC that I wrote on the previous page, and whether I'll evaluate whether J plus JCC has increased. And then from here, if J plus JCC is increased, and think of this as a cost, has increased, then at that point we stop, or we've gone in S steps, then stop. Otherwise, take next step. I'll say another run step. So at that point, you go back up to run. You do not redraw a new unit vector. And then that's what you do for every bacteria. So you do all that for every bacteria. And then at the end of chemotaxis, you repeat chemotaxis NC times. And you can view these as the lifetime of the bacteria. Yeah, I saw your hand first. Oh yeah, so that was just me giving background on the cellular mechanisms. So you can think of the clockwise as it's kind of this kind of dimension we're not worried about. So counterclockwise is equivalent to run, and clockwise is in terms of tumble. So I apologize for that. I can see how that can make it confusing. Yeah.
So basically, in that main run to the in that main loop that you do, we're going to keep going by step CI until we see that our J plus JCC goes down. That's what makes us basically go up more. But if we start going in the wrong direction, we only go there for a shorter distance.
Right. So, but because this is verb or so that the verbiage I use. So we say that bacteria climb nutrient gradients, but this is a minimization problem. So kind of flip it around. So it's you keep walking so long as it's decreasing. And at the instant it increases, or you've gone a sufficiently long amount of steps, then you stop.
Okay. So the moment we start going up, that's where I choose a new direction. But
right.
As long as I keep going down, I just keep up,
right.
Or a sufficient amount of steps, that's what makes it longer on the way down.
That's right. So if you're going downhill, you'll be in this run step for the full NS steps. And then the next time you iterate, go through the chemotaxis, you'll choose a new direction. If that new direction is not the same direction was before, if it's now going uphill, then you'll stop almost immediately, and then you'll draw a new direction again. And that's what gives you this run and tumble sort of feel, but it's more like tumble and run.
If I'm trying to maximize, do I need to add an offset? If I make it negative and change it to minimum,
there's no, in bacterial foraging optimization, because we don't calculate proportional fitness, there's no need for an offset. All you do for maximization is you just change the single J function here to be negative your optimization objectives. So I guess I can put that here. We could say use negative objective for J if maximizing. And yeah, no offsets are needed because it all compares relative. It says, did I locally go up or down? And it doesn't matter. All right, so that's the chemotaxis step. Yeah. Theta, you mean right here? That would have, they wouldn't matter as long as you're consistent, because that minus is sort of eaten up by this unit vector. So like if I choose a plus here, this might randomly be a negative, but if I choose a negative here, this might randomly be a positive. So yeah, it shouldn't matter. And so if you, for whatever reason, if like it just presents better to you if it's a minus, then it works exactly the same. Yeah. Oh, I see questions. I see the questions online too. I'll get to these right after this one. Go ahead. Yeah, so I glossed over some of the algorithmic things here, but absolutely, you would, so like before you move in a step, you'd save the current J so that you could do that calculation. And actually, I think I've linked the chapter in Passano's book where he talks about BFO. And in his algorithm, he goes through all of those ugly steps. Okay. I see some questions online. Let me make sure I get those. Sorry for the delay. All right, so after a bunch of increases in costs, the bacterium won't tumble and change direction again. Or does stop mean the chemotaxis would stop? So the stop here, this is stop for this bacteria. So to answer that question online, if this bacterium senses a cost increase, it will stop and the algorithm will move on to the next bacterium. And that will keep going. And once you're going through all of the bacteria, remember this is for each, or I guess I could say for all as well. So I have to highlight that. So this will go through all of the bacteria. So after you've gone through all of the bacteria, then you repeat the chemotaxis on all of the bacteria again. And other question, so this chemotaxis is applied simultaneously on all bacterium, and they all use the randomly drawn unit vector. No, so the this unit vector is unique for each bacteria. So I guess each bacterium. So every time you get a new bacteria, you draw a new direction. That one bacteria goes through all of its runs. And then when you go to the next bacteria, it draws its own new direction and then goes through for its runs. And so you keep, so this unit vector here, this random unit vector here, this is different across the bacteria. And then the next time you run through chemotaxis, it'll be different for the same bacteria again. So you keep drawing this every time you go into the tumble step for the bacteria. I think that was the most of that question. I thought there was maybe it was a second part. Oh, and then simultaneity. So again, if you look in Kevin's book, in the Passano book, he goes into greater detail about the scheduling of these bacteria. For computational simplicity, the way Passano suggests doing it is you consider so there's if you take a course on parallel numerical algorithms, you'll learn about a bunch of different ways to deal with these kind of multi-agent type systems, and there's different approaches on whether you like keep everyone's previous position and use them in everyone's calculations of their next, or if you keep kind of updating an individual and sort of everybody who's gone before, their kind of state is immediately updated and everybody's gone after is kind of later. And so Passano suggests for simplicity to do it that latter way, where I'm going to update the position of bacterium 1, and then bacterium 2 will use a J plus JC based on the old steps for bacteriums 2 through S, but the new one for bacterium 1, and so on and so forth. And so there's a bunch of different ways you could do the scheduling here of when this J plus JCC gets updated. It's just simplest if you update the positions in place. And so once I've done this for one whole bacteria, its new position will end up affecting the J plus JC for the next bacterium. So you could, if you wanted to, try to do this in a more simultaneous way, where you kind of keep, you save the positions at the top of the chemotaxis loop, use them for a J plus JCC on all the bacteria, and don't update the positions until the end of the whole loop. But it's not going to make that much of a difference. And so all of those kind of details on how you want to schedule the updates to the J plus JCC function, there are a bunch of different choices there. Like I said, the way Passano does is, which is kind of the easiest thing to do, is just as you calculate a new position, that new position becomes immediately available for all future calculations that may temporally seem out of sync, but it ends up not having that much of a difference. And then I think there was one last question. And that was I think all bacteria are processed separately. So yeah, you could imagine, again, there's different ways to schedule the updates for these things, but you can keep it simple and the algorithm's going to work it's a heuristic, it's a metaheuristic. And so getting we're not trying to model exactly what real bacteria do. We're trying to use these bacterial aggregations as inspiration for a way that we search through this optimization space. So, getting hung up on these little details isn't necessarily going to help the metaheuristic that much. All right, any other questions about the chemotaxis step? This is like the hardest step, the most important step, I guess, of bacterial foraging optimization. The others are kind of tweaking or tuning, kind of like going from ant system to ant colony optimization. Okay, so this is our chemotaxis round. So then we go through the reproduction round. And this one's pretty easy. We're going to base the health of a bacteria on the optimization objective that it has accumulated over its lifetime. So what I mean by that is we say for on each bacteria, calculate J, I'll call it J, I think superscript I, yeah, JI health equal to the sum, and this sum is going to go over the lifetime of this bacterium in its previous in the chemotaxis steps beforehand. So over its lifetime, let's look at just the optimization objective. So in this case, you'd have to keep memory of this or be accumulating this thing as the bacteria was going. So knowing that this was going on every time the bacteria is moving around, you can kind of keep track of this. So you're basically, notice there's no JCC component, it's just the optimization objective. So I'm showing it how much cost have you accumulated as you've been moving around in the space. And that is a metric for the health. And so here in this health sense, a larger is worse, smaller is better. And you can think of this as kind of a cumulative cost. All right, so now we can take all of those and we can just sort of sort all the bacteria, and we are going to kill the S/2 bacteria with highest J health. And then that's going to leave S/2 spots to fill. And so what we're going to do is take the remaining S/2, which were the ones with the lowest J health, and clone them. So then clone remaining S/2 bacteria in current positions. So basically, if you think about it in terms of position space, those bacteria that have accumulated a lot of cost, we knock all them off. All the bacteria that remain, we just clone them exactly where they are. So now there will be 2 bacteria standing in that position in the decision space. That's all we do for the reproduction step. And then we can then, at this point, repeat chemotaxis plus reproduction. I always want to drop the P in reproduction. In R times. And we can think of those like generations. All right, that's the reproduction step. So relatively simple. It adds selective pressure where we don't allow bacteria that are just kind of crawling around in high cost areas of the space to persist. We get rid of them and then restart. So we can think of this, is like selection in a GA. All right, any questions about the reproduction step? Let me make sure. I think there's a new question online. Question online is, does calculating the cost over the lifetime include all chemotaxis since start of the BFO or since the last reproduction? I mean, so I think typically we view this as just in the last chemo step, in the chemotaxis step. So we kind of, and we think of that chemotaxis round as the lifetime of the bacteria. So when you restart chemotaxis at the end of this thing, it's almost like all the bacteria are starting anew. They just were born in that area. And so they're kind of J-healths are reset. Okay. Any other questions about this step? And then the last step of BFO is elimination dispersal. Elimination hyphen dispersal. And so an elimination dispersal for each bacterium we are going to flip a coin and say with probability PED, which is another hyperparameter, disperse bacteria I to a random position. And then we just repeat the whole process. So chemotaxis plus reproduction plus elimination dispersal in B times. And so if you think of the chemotaxis as kind of a fine-grained mutation, sort of a gradient descent, kind of a directed random walk or a correlated random walk, then this is a coarse-grained mutation. So it's sort of an undirected mutation where we just randomly, with some probability, everybody gets mutated to some random position and gets to start there. So that's another way to add diversity to the system. And you could imagine further embellishments. Could imagine, sort of a sexual, a reproduction where dispersals land in between two other bacteria. So there are different ways that you could play with this approach. But that's the basic approach to bacterial foraging optimization. It's just another approach that moves around continuous spaces, that tries to be a little bit more intelligent than a GA, while still having a lot of the same selective pressure and mutation that you see in a GA. All right, so any questions about BFO? Yeah. Well, so bacterial foraging optimization isn't one that you're going to see as commonly as some of the others. It has a lot of hyperparameters, so you can really tune its performance. Very often, these hyperparameters are kind of set as degenerate versions of each other. So I think, like I mentioned, you often set. I think I've got some examples of the. Like I think a common way. What I got? Yeah. So like you commonly set like the H repellent and D attractant to each other. So like there's a couple of things that make it so it doesn't actually have quite as many hyperparameters, but I don't have like a great, like I can say that BFO is particularly like, so much better than X, Y, or Z. The big reason I put it up here is to me, it fits very well in between ACO and PSO, which are two, when we're going to talk about PSO next. So it's got the chemical communication between them, and it's got actually movement through space, whereas ACO doesn't have real movement through space, but we're starting to see this kind of physical coupling. And it is inspired by bacteria searching around, which a lot of these algorithms are either inspired by the very small, the kind of genetic algorithms, or the very large, like flocking birds and things like that. So I thought it's kind of nice to be in the middle. And I have kind of a personal affinity for it just because I have it's in my academic lineage. But so if you went to another course that was like this one where they talk about BFO, I don't really know. So I don't think it's probably been studied well enough to characterize that. But I think it's a relatively straightforward algorithm that at least in Kevin's example seems to work pretty well. And it's kind of looks, if you plot it out, it's kind of neat because you can plot these kind of potential functions. That's effectively what this is, kind of a big potential function. You can kind of, you could plot this in space, and there are these wells that move around that are kind of centered on each bacteria. And it's kind of just it's an interesting algorithm to visualize because you've got not only the general shape of space, but then it's like these like little points of gravity. Like you got these planets that are moving around, deforming space around them. So you've got like the sun isn't moving, and so that's like this becomes this kind of like gravitational well due to the sun, and then each one of these little mobile gravitational wells that are moving around with the bacteria as they're all trying to approach the sun. So it's just kind of a cool visualization. But and you can see some of those 3D visualizations in the chapter, I think, that I shared online. Online here, any questions? It's just a confirmation. All right, so that's BFO, inspired by E. coli, meant to be kind of a mixture of the kind of chemical communication in ant colonies with the population dynamics we see in the GA. All right. So with that, I'd like to introduce the last algorithm that we're going to talk about for swarm intelligence, particle swarm optimization. And it is something that if you work in neural networks or anything now, a lot of, you might be familiar with or off-the-shelf algorithms for optimizing neural networks, like stochastic gradient descent, that have these terms like momentum that are added in them. And these ideas about momentum and its so-called regularizing effect on optimization of neural networks come from the sort of particle swarm optimization perspective. And so, so this is kind of where some of those things are kind of grounded. But so before I move on, are there any other questions about BFO? Clear? All right, so from here, this is basically kind of our introduction to particle swarm optimization. Which then in the last lecture on Tuesday, we'll finish up on. And so PSO is pretty popular. It works pretty well. It was, as I'll talk probably more about next time, PSO was developed because people wanted to start applying things like genetic algorithms to neural networks. And as the neural networks got bigger, the genetic algorithms got a little squirrely. And so what I mean by that is there's so much space to move. You're talking about, I got, thousands of weights in this neural network, and each one of those is a decision variable. So the dimension of this search space was extremely large. And so if you just had a genetic algorithm, it could pop up anywhere. Wherever it got kind of a hint that there was a slightly better performing network, it would then go and investigate that. And so you'd get these it was difficult for the algorithm to just kind of settle down and find one spot for it to exploit. And so it's kind of like I mentioned, for those of you that are familiar with this, and we'll get into this next unit when we start talking about neural networks more formally. For those of you familiar with using these off-the-shelf tools like stochastic gradient descent to optimize neural networks, there are these regularization components where not only do you have your loss function, which is kind of like encodes the problem that you want this network to solve, you've also got these regularization terms which have nothing to do with the problem you want to solve, but they just are meant there to tame the algorithm, the optimizer, so that it doesn't go crazy, it doesn't go everywhere. It sort of keeps the weights kind of close together. So it's kind of like there might be another set of solutions that work just as well as these solutions. But if you've already found something that kind of works well, just stick here for a while. I don't want you to actually go and investigate way over in some other space in the decision space, unless the current solution really isn't working well. And that's what particle swarm optimization was meant to be, kind of a way to say, can we use something that's more physically embodied to kind of capture those same types of ideas when we do optimization? And so PSO is built on the idea of with still like bacterial foraging, we've got particles moving in space. But now instead of thinking of bacteria kind of floating through space, think of these like birds that are flocking. And that these birds, you know, they've got position and velocity, and they cannot turn on a dime. So they can gently turn towards other birds, but most of the time, you know, they're going to go in pretty much straight lines. So they're rarely going to turn around and go straight backwards. And they're certainly not going to disappear in one spot and reappear in another. So they follow smooth trajectories. And so we now have dynamics that we're basically going to apply. So imagine we have these particles which have position and velocity. So you can imagine that they've got position, I'll say for particle xi, I'll say its position at t+1 is its previous position plus some velocity vector. And then I've got its velocity vector at t+1 at the next time step is going to be its previous velocity which I'll scale by some inertial term, plus, and this is where the bacterial foraging starts looking similar, plus basically attraction and repulsion to individuals around it. Now, there aren't arbitrary individuals around it. They're individuals that have been identified as currently finding the best solution, and including their own historical best solution. So you basically can have plus B times and I'll write what these are in just a second. RS. And then down here, imagine this is on the same line. I'm gonna, for simplicity, because we'll get into this in more detail, I'm just going to call this, yeah, all right, I'll call it xjt minus xit times r. Probably should use another letter other than T. I'm going to just call this one that I said RS, I'm going to call it RA, and I'll call this one RB. And so what this here is, this is the position of agent I's best performance so far. And this is the position of the best performance, or the best performing individual right now. And RA and RB are random numbers drawn from a uniform distribution from 0 to 1. All right, so this is the basics for basic particle swarm optimization is like bacterial foraging optimization, but instead of moving around with that complicated run and tumble, they're moving around with this kind of approach here. So this alpha here is an inertial hyperparameter. You know, think mass. So the idea here is that, let me make sure I didn't leave anything out. So the idea here is if alpha is equal to 0, then this thing can sort of change its velocity instantaneously. If alpha is, or A, I guess is, I think I'd actually have written down as A, but we'll call it alpha here. If alpha is very large, then the previous velocity has a large impact on the current velocity. But the velocity is also influenced by the position where it last experienced the very best of this optimization objective, and the position of the agent currently who's sitting at the best position across the whole swarm. So that's what these things are here. These are distances where if you are, this will bring you toward your best position, and this one will bring you toward the agent in the swarm at the best position currently in the swarm. And so we can scale those. And so these B and C are hyperparameters. They're just positive hyperparameters. And RA and RB are just random numbers. So that every iteration through, you draw a new random number. And so this gives kind of a little bit of a randomness, so a little bit of a stochastic search field to it. But the overall thing here is that particles will tend to move in the same direction they were moving in, but then they will be grabbed by they'll be attracted back towards positions that were high performing to them. And they will also be attracted to positions of others who are currently high performing. So notice that nowhere in this update rule is the optimization objective's value. It's just the position of where the best value in the history of the current one is, and the current agent at the best value currently. And this is kind of the essence of basic PSO. You're just constantly attracted to these positions. Now, as you're searching, these positions are going to be updated. So if you happen to find a better position, this anchor gets moved to that better position, and that gets moved instantaneously. If another agent tends to suddenly, you know, like the best agent is like all the agents are moving around, but the one who's best might suddenly change as well. And so these things here, these references in the middle, these can change instantaneously. And so they're kind of like these instantaneous updates that get filtered through this dynamical system here. This is like a single integrator where you're like, this is kind of like an acceleration term that gets integrated into velocity, I guess a double integrator, and then this velocity gets integrated into the position. So the influence of these instantaneous changes takes a little while because it has to manage to change the velocity of the current particle, and then from there, change the position of the current particle. And that gives this, this system a feeling of momentum, which has kind of a regularizing effect on optimization problems like neural networks where you kind of don't want to be jumping around the space whenever you get a hint that things might be better elsewhere. This sort of, it reduces large movements in search. So now, if you really want to search far away, the whole flock has got to drift far away into other spaces. As opposed to in the GA, you could have some members of your population over there, some members of your population there. There's crossover that happens. Suddenly you have some that are here, and they're just constantly bent down, going all around the space. Here, you get clumps of agents that are searching together. And that's kind of the essence of PSO. So I'll get into details about that next time. I will say that PSO has a wide range of offshoots. We'll talk about some of them. You can imagine different ways to embellish this. Like I could focus on the best position in my local neighborhood as well as the best position in my global neighborhood. So there's the kind of local best and global best. There's other things that get rid of the randomness. So these random numbers here. There's like one I reviewed an article once, I think, on a chaotic catfish PSO that was based on the idea that you could replace these random numbers with chaos, which is a deterministic generator, so that instead of having to go out and draw random numbers, you could have a simpler system that is more computationally efficient that manages to do the same thing, but it might actually not only be a little more computationally efficient, it actually might have these ergodicity parameters where it helps to guarantee that the PSO is space filling, so that you not only are searching locally, you're guaranteed to eventually search the whole space. So there's those sorts of modifications. And then there's things that do adaptive inertia. So this inertial parameter here, I'm assuming it's a constant hyperparameter, but kind of like a step size that you might want to adapt over time. You can make this inertia kind of stiffer and weaker over time. And so maybe initially you don't permit a lot of rapid changes. And so this inertia is very large, the mass is very large, but then over time the mass gets small and then it's allowed to make these small changes. So once you're confident that everyone is going to stay around a position, then you can make this small, and then that way they can kind of fine tune in that area. And so rules for updating this inertia. So there's a bunch of different ways in which you can make PSO better or different at least. And we'll talk about that a little bit, but this is kind of the basic essence of it, is that it's sort of bacterial foraging like, but there's no cost function that shows up directly in the motion rules. It's only the updates of these positions that reflect the actual cost function. All right, and that's all I've got for you. Any quick questions? If not, don't forget, form your teams, concept check 5, mini project 4.
What are B and C?
B and C are just hyperparameters, so these are positive, so we would make these greater than 0.
So could we lump them with the RA and RB somehow?
Well, so the RA and RB are meant to be that these change, these are drawn every step. So RA and RB are, you could adjust this probability distribution so that instead of going from, this is basically, you could lump these together and say this is a random number from 0 to B.
0 to B, yeah.
Right, but then you still got to choose what the B
Right.
is. Right. So, all right, any other quick questions? Well, in fact, if you guys, anybody needs to go, you can go. I'm done, but I'm happy to take questions. Is there yes, there are questions. Can XI, yes, you can be the best. And if you're the best, then these two things might be zeroed out. So then this gives you kind of encouragement to move towards your past history, which might be your current position, it might be a past position. So yeah. Any other questions in class? Yeah.
It's not super related to this, but in a few of the lectures, you said something along the lines of, like, for example, like that incoming optimization or other algorithms are a little bit like cartoonish, like they make some assumptions that are true in biology.
Mm-hmm.
And so I'm kind of curious, like, what is your opinion on, like, when these algorithms are kind of artificial? Like, are there times where it would be better if they were more biologically accurate, or is it beneficial for them to sometimes be like make artificial assumptions?
Right. So the question is, and I'm just making sure there's not, I mean, to make sure there's not a specific question. So online, if you're still online, B and C, question about B and C. B and C are just, they control the sensitivity to how attractive the individual is to its past performance and other individuals in the swarm. So if you want somebody to hang closely towards how well they've done in the past, you update B. If you want them to hang closely towards the best current individual, you increase C. And so there's it's sort of tweaking the it's tweaking those sensitivities. So I don't hope that answers the question. Let me make sure if even the question answer is still around. Okay, great. Any other questions online? If not, I'm going to go in the meeting. I had sort of a slightly more off-topic question in class, so. Okay, see everybody next week.